All right, everybody. So today we are going to actually take a look at a few examples with solving one-dimensional kinematics problems. I have a couple of calculus-based problems already ready to go, so we can just focus on solving those. And then in addition to that, too, we can also take a look at a couple of like sketching graph problems as well, too, because I think that'll be something that's good for us to cover, especially when we're thinking about problems like the translation between representations for your response question and for some good multiple choice question types. So on the screen, you can see one problem. A car is undergoing acceleration given by a of t is equal to 6e to the negative t. And we're also, notice, given some information about the initial velocity and the initial position. We're told that the car starts at the origin and that it starts at rest. We actually do need both of those. You may remember from the last video we were talking a little bit about like our initial conditions or our integration constant, how you get an extra constant when you integrate. So we are actually going to need those two pieces of information to completely solve this problem. Now, in addition, on the screen, you should be able to see the calculus portion of the AP Physics C equation sheet that is provided to you on the AP exam. So you are given this. So I'm going to kind of show you how we would maybe work with that as we're solving this problem then too. So let's go ahead and get started. We're given acceleration. We're told to find velocity. We're told to find position. So we do know that velocity is the integral of acceleration, and then position is the integral of velocity. So we can start off by writing v of t is equal to integral of acceleration as a function of time with respect to time. So that's going to give us integral of 6e to the negative t dt. Now, much like with derivatives, we kind of took a look at something in the last video with us being able to essentially ignore constants out front for derivatives. You can do the same thing for integration because integration is like a multiplication. It's like it is literally the area under the curve of the function that you are trying to integrate. So in this case, 6e to the negative t, we're taking the area underneath that graph. And so that's the same thing as pulling out the 6 and then taking the area of e to the negative t. So let's go ahead and do that. So we get 6 integral e to the negative t dt. Now, look at the calculus portion of our equation sheet. Only one of the integrals actually has e in it, and that's the second one. So that means that that is the one that we are going to use in order to actually do this integration. You can see that if you have a power of a, you have to actually take out a 1 over a. So then what we have to do is we have to figure out, well, what's the a in our function? It's negative 1 because of that negative sign. So we get negative 6 e to the negative t plus our integration constant. We're going to call this one C1 because when we integrate to find position, we will actually have another integration constant. First things first, before we actually solve for position, we have to figure out what C1 is. Well, the initial velocity is going to be 0. So when I plug in 0 for time, my entire function should vanish. It should go to 0. Well, e to the 0 is 1. So we end up with negative 6 plus C1 is equal to 0. Therefore, our value of C1 is going to be positive 6. So what that's saying then is that the full velocity as a function of time is given by 6 minus 6e to the negative t. In other words, excuse me. In other words, as t goes to 0, when t is at 0, right, the initial point in time, there's no velocity. The car is at rest. But if you take the limit as t goes to infinity, right, go a very long time out, that second term is exponentially decaying, so it's going to essentially go away. And the final velocity, right, the velocity as time approaches infinity, as this car has been moving for a very long period of time, will be 6 meters per second. So we can integrate this function once more to find position. How we do that is we can actually split up the integration. We have two terms in our velocity, 6 and then the negative 6e to the negative t. The good news is that we can actually split them up and do the integration of each one separately. So let me go ahead and write it out just to show you what I mean. Right, we start out by integrating the velocity. I probably should have written that down. Integral of v of t dt, right? That's important so that College Board or whoever is grading your work knows what they're doing, right? So what this is, simplifies to, right, or if you split it apart, you get integral of 60t from the first term minus 6 integral e to the negative t dt from the second term. Whenever you're integrating just a constant, so that's 6, you're just going to be able to multiply it by t. So you're going to get 6t from the first term. And then if you do the integration of e to the negative t again, that's going to cause the second term to become 6e to the negative t then. Essentially, that negative sign we got from integrating our acceleration will go away because it'll cancel with the other negative, another negative sign that we have to pull down. Good. And then we have plus C2. All right, same deal. X of 0 is equal to 0. I'm going to scroll down a little bit just to make sure that we have enough room. Oops. Ah, weird. I apologize. It's not wanting to scroll down for some reason. There we go. All right. Perfect. Okay, so x of 0, right? When you plug in 0 for t, your position should be 0. 6 times 0 is 0. 6 times 1 is 1. And then C2 is what we're trying to find. C2 is going to be negative 6 from that equation. And therefore, x of t will equal, I'm going to pull out a factor of 6 so I don't have to keep writing that because my laptop is kind of lagging a little bit. So 6 and then in parentheses t plus e to the negative t minus 1. And that is your position as a function of time then. One interesting thing to note, or perhaps not so interesting, what you should expect is that the position is just going to keep rising and keep rising and keep rising. It's never actually going to level off to some value. That should be expected because if the velocity levels off at 6 meters per second, then our car is just going to keep moving and keep moving as time goes on. So it should not level off as time goes on. But that's good. There's our position. And then, of course, we found our velocity earlier. For some reason, it's not liking me scrolling back up. It keeps zooming in and out. So, yeah, weird. Okay. Anyway, our velocity is 6 minus 6 to the e to the negative t. All right. For the second one, I invite you to kind of use what we know about functions if you want to, right? If you want to try that one out, feel free to pause the video and then you can resume it, right? But yeah, let's go ahead and take a look at how we can solve that one. So a car's position is given by that function there, negative 4t squared minus 6t plus 3. We want to find the maximum velocity of the car. So how are we going to do that? Well, maximum velocity, right? We can think about that in terms of calculus. Let's start off by focusing on what it would mean for things like maximum position, for example. So maximum position occurs when velocity is 0, right? And we know that velocity is derivative of position. So therefore, we might be able to infer, and in fact, it is true that maximum velocity is going to occur when the acceleration is equal to 0. So we have to actually find a as a function of t and set a to 0 and figure out when that happens. So taking the derivatives, right? If you have a power, so a polynomial, do each term separately. So dx dt. And then you essentially pull down the power and reduce the power by 1. So you pull down the power of each term, and that becomes like part of its coefficient, and then you reduce the power by 1. So dx dt, right, Well, derivative of negative 4t squared will become negative 8t. So you can see that we've pulled down that factor of 2 and then reduced the power by 1. And then the 6t, the derivative of that is just going to be 6. The derivative of plus 3 is going to be 0 because that's t to the power 0 then. Going back to that negative 6t, well, that's t to the first power. So you're pulling down a coefficient of 1, reducing the power to 0. T to the 0 is 1. So hence you get negative 6 for that second term. Taking a look at, I probably should have done a cubic function actually. I don't think this is going to work. Um, A of t is actually just given by negative 8 because that's the derivative of velocity for all points in time. We kind of have an issue there because because that function kind of never your acceleration is never going to be 0. However, there is one important thing to check, right? It does kind of seem like we're lost. But in all of the problems that we typically solve with our AP style questions, your time is typically bounded by being non-negative. So you typically start at t is greater than 0, right? And then you just keep going until t is positive infinity or whenever your object stops moving. So if if our acceleration is always negative 8, then either our maximum velocity is going to happen at the beginning of time or the end of time, because we're just going to keep accelerating as time goes on. Well, if you plug in t is 0 for velocity, so the velocity at time t is equal to 0, right? That's just going to give you negative 6. If you plug in t is going to infinity, your velocity is going down to negative infinity. So that means that our maximum velocity is just going to be negative 6 meters per second. It actually happens right at the start. I didn't actually, intend for that to happen. Again, if you were asked to actually solve for maximum velocity, the general procedure is to figure out what time the acceleration is 0 and then plug that time back into your velocity function. So let's say, for example, that if the acceleration was 0 at time 2 seconds, right? If you plug in, if you say that a is 0, solve a of t for time, plug 2 seconds into v of t, then whatever that value, whatever that function gives you, whatever v of t gives you when t is equal to 2, right? Again, just as an example, that would give you your maximum velocity. But for this problem, that doesn't happen. Your acceleration is always negative, right? So because our velocity starts negative, keep in mind that if you're moving to the left and you're pushing the object to the left, right? If the car is moving to the left and it's accelerating in the negative direction, it's just going to speed up. And that velocity is getting lower and lower and lower because negative 6, right, is greater than negative 7, so on and so forth. Negative 6 is the least non-negative number, the most non-negative number, excuse me, that you have. It's the number that's highest up on a number line. All right, so there we go. Let's take a look at a little graph then too, just to kind of show you what some sketches look like, and some important features for graphs. So I'm going to go ahead, draw just a very rough sketch of a position time graph. So let's say that we've got x, t, and maybe our position time graph looks something along the lines of this right here. All right, wants to keep lagging. I apologize about that. It's supposed to be like a nice smooth curve. Didn't really work out that way, unfortunately. My technology is not quite up to where it should be. So if I wanted to ask you to sketch the velocity as a function of time and the acceleration as a function of time, we could do that. The important thing with velocity and acceleration is that we just essentially want to know when is our velocity and acceleration getting farther from 0? When are they getting closer to 0? Are they positive? Are they negative? Right? Are they lines? Are they curves? We should be able to pick out all of that information. We know that velocity is the slope of position time. So whenever position is increasing, velocity is going to be positive. Note the first part of our position time graph, right? Up to from 0 to about this time indicated on the time axis here. Your position graph is getting steeper. So what that means is that your velocity should be getting farther from 0. Your car should be speeding up, or whatever object you have should be speeding up, right? Is that going to be a line or a curve? We can't really tell based on the function. Right, if you're given an actual function, you'll be able to tell, but just with the general shape, you just have to get the correct trends out of it, essentially. We don't necessarily know if this is a bunch of quadratic functions or not for position. Let's assume that they are, just for simplicity. Derivative of a quadratic function, right? We saw in the previous example, that's just a line. And so velocity would just be a line then, because that's the derivative of position. Take the second part of the graph then, up until position reaches a maximum. Well, position's still increasing. You're still going to have positive velocity, but now your position is leveling off. Therefore, you should expect that your velocity is getting closer to 0 because your car is going to be slowing down. Right? The slope is getting closer to 0 based on that graph, the slope of your tangent line. Go to the next part, right? And you'll see that your car is going to be speeding up in the negative direction because position is decreasing at a increasing rate, right? It's getting steeper, and then it's going to flatten back out, and your velocity will go to 0. Right. So essentially, so here are the important things, right? Number one, whenever position is increasing, velocity is positive. Whenever position is decreasing, velocity is negative. Number two, whenever position is a minimum or a maximum, velocity is 0, right? Those are our turning points. That's when your car is reversing direction. And then if we want to sketch the acceleration as a function of time, we can gain some more information then as well, right? So let's go ahead and sketch that actually. Acceleration being the derivative slash slope of the velocity time graph should be a little bit easier to draw, right? If velocity is a line, acceleration is going to be constant along that line. So look something along the lines of this, no pun intended there, right? Two positive accelerations for when the velocity is going up, and then a negative acceleration for when that velocity is going down. Something to note for the acceleration graph is if you're not sure what sign the acceleration should have, look at the direction your position graph is curving. Note that in the first and the last sections of your position graph, it's curving upwards. It's open upwards. We call that concavity, right? So we would say that position is concave up. It is open upwards in the first and the very last intervals of the graph. So that would yield positive acceleration, right? That includes positive velocity and speeding up, and negative velocity and slowing down while slowing down, right? And then the two middle parts you can see are curved down, they're concave down. That's negative acceleration, encompasses two scenarios: if you're moving in the positive direction and slowing down, or if you're moving in the negative direction and speeding up, both of which are happening, right? So note that the acceleration graph alone does not tell you what direction you're moving, but the velocity graph does. So as you go from acceleration to velocity to position, you're essentially gaining more information. The position graph tells you the most about the object, right? It tells you where you're located. You can figure out how fast you're going. You can figure out how your object is being pushed based on concavity, right? Whereas if you take the velocity graph, all you can determine is how fast you're going and in which direction, but not directly where you're located, unless you know an initial or the position of the car at some point in time. And then the acceleration graph, the only thing you can really tell is what direction is the car being pushed. You can't tell how fast it's going unless you have more information just by itself. You definitely cannot tell where the car is located with just the acceleration graph and no other information. All right. So a little bit of graph stuff there, right? A little bit of stuff with functions and manipulating them, doing some derivatives, integrals, right? There's loads of questions that could be asked with that, like find the velocity as a function of time, find acceleration as a function of time, find position as a function of time, right? You could be asked for things like average velocity, which would just be displacement over time between the 2 points that you're actually trying to find average velocity for, right? You could figure out your maximum position, right? Again, take the derivative of position, set that equal to zero, because a derivative has to be zero when the function is a maximum or a minimum, right? Yeah, there's loads of stuff that calculus actually opens the door for. So as we're kind of going on throughout the rest of this course, you'll kind of see that we will be kind of doing some examples here and there. But thank you guys for watching. I think that about concludes what I wanted to talk about for this video. So in the next one, we will continue on with our topics. We'll actually be talking about relative velocity, which kind of goes back to thinking about vectors and scalars. And then after that, we'll end off kinematics by talking about two-dimensional motion, focusing on projectiles and parametric equations, things with x and y components that both vary as time goes on. All right, have a good day, guys. I'll see you in the next video.